Welcome everybody to the flight safety review portion of the program. With us today we have Tony Alcocer, who is our flight safety officer, who has complete responsibility for anything flying at the spaceport in terms of it being safe and having gone through an inspection before we let it get to the motor. And, you know, we do the flight safety reviews. Tony has responsibility for that, but a lot happens in between when a flight safety review is done and the rocket actually comes to be brought to the pad. And so that's where Harry comes in. Harry Spears is our final flight safety review officer, and you know he'll do a final once over on your rocket before you head out to the pad or get assigned a pad. And Holly, you like to introduce yourself, and then
so I'm Holly Gummels. I'm going to be moderating today. I'll be helping out with the Q&A section. So if anyone has any questions during this section, please put them in the Q&A section to the right, and we'll address those at the end. You guys want about 10 minutes at the end for Q&A? Does that sound good? All right, we'll do that, and I'll try to help with the images as well.
Great.
All right,
So,
I'll go ahead.
Tony, over to you. Yep.
All right, sounds good. So up to this point, we've seen your applications. We've seen probably 3 progress reports. And hopefully we've been in contact with you asking specific questions on shock cord size, weight, lengths. If your SRAD motors were asking about burn sim files and test fires and all that stuff. And so we've only read or seen photos and videos of your project at this point. Once you arrive at Spaceport America in Las Cruces at the science fair, you're going to be going through a flight safety inspection where you bring the rocket in, all the pieces except for the energetics, no propellant, and no deployment charges. And we're going to actually able to squeeze the rocket, poke it, and measure it, and talk about it, and seal it, and see all that stuff for the very first time. And so we're always asked ahead of time, what are we checking and stuff. And I don't know if you've watched the video that I put on YouTube recently, and the title on YouTube is Spaceport America Flight Safety Inspection, I believe. And there's some links in the description, and in that you should have a document that actually tells everything that we're looking at. There's several pages here. There's a checkoff sheet that our people use sometimes when they're new. They go through this, and it's about 3 pages. And nothing of this is hidden from you. You all have access to this. And so if you've been to a normal rocket launch, you're going to see them asking you a lot of questions. But in this case, they're big, heavy, powerful projects, and we're literally going to look at them from the outside, inside, asking a ton of questions. We're going to be asking your electronics people, your motor people, tons of questions and stuff, just for us to be comfortable to let that rocket fly. It's kind of rare that we find a project that has no issues with it. And maybe we want you to put a bigger flat washer where your forged eye bolts are going through the bulkhead just so that it doesn't pull through your 3-ply plywood bulkhead. The biggest hurdles to overcome are projects where the fins are too thin or weird shape and not attached properly, and we can bend them. If we can bend your fin, it's probably not going to fly. Luckily, in Las Cruces, there's a Home Depot. They do have fiberglass. They do have epoxy and JB weld. We can help you doing kind of a makeshift repair and hopefully get those things stiffened up so that you can fly. But occasionally, we just can't fix what you bring us, and you're going to have to sit that flight in this contest out. So if you have any questions while I'm yammering and stuff, please put them over there, and Holly will stop me and say, hey, so-and-so has a question. So if anybody watched the video already, and there's been about 300 views, and you have questions about the video, please ask them now. I get tongue-tied, I get absent-minded. There's lots of things I say that I wish I hadn't said. There's things I wish I had said. And so actually I have 2 video cameras, and I can actually do another really quick flight safety review on a rocket that I have. I had it outside this morning. The sun was shining the wrong way. I had a really bad blur problem. I wiped that for a couple hours. I'm in on our kitchen table, and the other camera sitting on a shooting through the doorway that's currently open. So if you have any questions, ask and stuff. Let me get to the other video, and all I'm going to do is kind of go through a quick flight safety review with the rocket that's in front of me. It's a 6-inch rocket. It weighs about 50 pounds. It flies on a 4-grain M motor. It goes about 15,000 feet, just under Mach. And I'm going to try to change cameras. I don't know if no questions is a good thing or a bad thing. There we are. So its tight quarters are right here. So one of the things we start with when I see a rocket is my general impression of the rocket, the length, the diameter, and the fin span. Does it look good? The workmanship, what do I think? The ratios to the fin length. And so one of the things that we like to see is the diameter of this rocket is 6 inches. So we'd like to see fins that are at least 6 inches span. We're looking how well the attachments for the rail buttons are, and we'll get back to those in a little bit. Looking at holes in here. We're looking for shear pins, vent hole for the electronics, vent holes for the compartments, and anything else that's on the outside or exterior of the rocket. I have a bunch of things behind me. So one of the things that is kind of uncommon is we find some rockets that have aluminum tips, and they have a very simple eye bolt and a washer. When these aluminum tips heat up, they get a little bit bigger, and it's possible that they become offset. When they become offset and you end up with supersonic air going into the nose cone, the rocket doesn't usually finish its flight profile. So is that video camera angle working for everybody? Is it okay? Yes? Okay. So on this rocket here, my apogee compartment is down here. My other parachutes are up here. So I'm going to go around the table and I'm going to get down near the fin can. So we're going to check how strong the fins are. These are 8-inch aluminum fins. They're bolted on 8 bolts through to an aluminum fin can assembly inside. My motor is not going to shoot through the rocket because it has a snap ring on the outside pushing up against the aft end of the rocket, and it's bolted in place up here in a coupler. I have 3 fins. They look like they have enough span to provide guidance to the rocket and the flight profile that I've chosen. So when I get up here to this first coupler, I want to see what kind of shear pins they're using. At least 3, like 430s for this size rocket. I'm going to wiggle this to see if there's any play in this coupler. Does this look weird? So my rocket's apart. I have my recovery gear in here. I'm going to check what your anchor point up here. I have a 5/8 or a 5/16 muffler clamp through 3/4 inch plywood desk up here. I'm using 1-inch nylon recovery harness. There's 35 feet here. I have a Nomex blanket that protects the parachute. This is my drogue parachute. And my recovery gear. So if you're using nylon, you need to protect it. And what you can do is use a shorter piece of nylon that's tubular and put one piece inside the other, or you can take duct tape and put duct tape on it to protect it from the charges going off. Another thing that I like to do is put brake points in here. And what those do is it helps cushion. Go up and let the drogue parachute deploy. They're simple, made out of duct tape or electrical tape. And I put this tape on as tight as I can. And this will take about 60 pounds to get it to release. And so I have several of those. But I'm losing the kinetic energy by it having to pull through that tape. So that's the kind of stuff we're looking for. My main parachutes, I actually have 3 of them. This is just a sport rocket. Again, that there's no play in this. That my recovery gear is protected by Nomex. And we have 3 chutes in here. These are the Aerocon 60-inch chutes. Again, this is just a sport rocket that I fly. We're going to be taking a look at your electronics. This one has a hatch that I open up. No questions yet?
Well, there is one question, and that is thoughts on rockets where the stability margin changes a lot due to depleting fuel and shock waves.
Yes. Why? Or what was the first part of that?
Well, what's your thoughts about the changing stability? Thoughts on it is, you know, as long as you've got enough margin to keep it stable.
Yep, I'll talk. Hang on. So I think the question is about stability margin, fuel burning, and the center of gravity changing.
Yeah.
And so, yes, that all happens. And originally, when I got into rocketry, people, at least one caliber being the diameter of your rocket, 1 caliber long from the center of pressure to the center of gravity. But rockets do fly like that. But if you hit a wind shear, if you have the nozzle plug up for a little bit or something, it doesn't have the recovery ability that a rocket that has more calibers of stability. So one of our rules, and Harry, correct me if I'm wrong, is that we require you to maintain at least 1.5 calibers of stability throughout the flight and stuff. So then along comes CTI with their N58, is it 58 or 5600 motors?
5,600.
5,600, they have an altitude contest for the highest minimum diameter rocket. I can't remember how many rockets either lost fins, the nose cones imploded, or the rocket simply switched ends right about motor burn now. And so the ones that were interesting were the rockets that switched ends. It wasn't like a fin came off. Flights, the fins, all three of them were still on it. And so the best I can say is that, yes, as the motor burns, burning up the propellant, the center of gravity is going to change. The center of pressure or center of drag is going to change on those fins too. Does that make sense? The faster you go, the more drag that fin is. And between those two things, changing values in a very, very fast period of time, it's almost like me running towards you and trying to stop. My brain says stop, my body says stop, but momentum carries me on beyond where I want to stop. And so those two forces, yes, and the rocket just flips end for end, basically.
Well, and you've got your center of gravity would be moving forward and your center of pressure would be moving back, right?
Yes, and if you sit down and start using logic and stuff, wait a minute, Tony's completely wrong, but something happens there. And the fix is fairly simple. Fly with 2.5 calibers minimum, and it won't happen and stuff. And so I'm fortunate that I fly out at Black Rock. It's my home field, and I see a lot of record attempts. And I call them record attempts because there's a lot more attempts than there are records being set because the fins are too thin, too flimsy. The calibers of stability aren't there. And it's so I built a rocket that I call an Aeropack is the club I belong to, and I call it an Aeropack Sport Flyer. And I have a similar one here that I use for STEM. And so the trick is to have fin span, which is from the body to the tip of the fin, called the semi-span. And I want at least 1.1 calibers of span, not 1, but 1.1. And believe me, that 0.1 acts a little bit. It keeps your fins out in that cleaner air when you're going from Mach 2 into Mach 3 and stuff. And then for my calibers of stability, that I want at least 2.5. And so I'm going to hold this rocket up just a little bit. And this rocket flew a couple of weeks ago. It was put together by a high school STEM program that I teach. And we kind of messed up when we laid up the body tube that it should have been a little bit longer. And so to fix that issue, the electronics are in the nose cone, but we had to put 5 ounces of lead in the nose cone and then 6 ounces of lead on the bottom of the electronics. So we have 10 ounces of lead in this nose cone alone to keep 2.5 calibers of stability. This was an attempt to set the school's speed record. It flew on a J1800. And so along with this extra weight in this nose cone, and we put 2 632 nylon screws. I think you can actually see one still through there, shear pins to keep it from shearing off because it's so much lead in this thing. I think I'm getting off base. Okay. Sorry.
We do have more questions though.
Okay. All right, go ahead.
Next question says, I see you have blue tape on the couplers to help with the fit. For competition, is that still an acceptable method for getting the coupler fit correct?
Yes. I don't know where you live, state or country. I don't know the humidity or temperature where you built your rocket. And currently, I want to say it's 110 degrees at Las Cruces Spaceport, America. Something is not going to fit. because of the heat, temperature, or humidity. It's easier to add tape for that as compared to having to sand couplers the entire length and diameter. And so I would rather have to add tape to something to get it to fit just right. And as you're machining these parts, I don't have anything with me, but like aluminum couplers or whatever, think about where you're taking them to be used and where you're making them at temperature-wise. And if you have a 4-inch rocket that has an aluminum coupler that's a very nice fit from Alaska, and you get to Las Cruces, it's not going to fit. Make it small to begin with anyway, and then put tape, and it maybe there's something better than blue painter's tape too out there. So.
Yeah, that thermal expansion is a real killer out in the desert.
So yes, and so my son, who got me into high power rocketry like 20 years ago, got us into using the motor as the coupler. And so the first time we tried it, we had a little piece, like a 1-inch piece of masking tape on the motor case because it was pretty sloppy and stuff. And we ended up crashing because tape and on motors get warm and it just wouldn't separate. So there's a fine line when you're using an aluminum tube that's going to get hot from the motor burn plus hot from wherever you are. It's just a really iffy situation using the motor case and
glue.
Yeah.
Yeah.
So,
yeah.
The tape sucks.
Yeah. So there's a follow-up question on that stability question. What are the risks of overstability?
And years ago out at Black Rock, Dave Griffin, I think his name is, with Wrap Motors, a hybrid, he came out with a 2.5-inch M motor. And you can imagine a hybrid motor that has kind of low SP, super, super long rocket. And he had 14 calibers of stability just because that's what it took to get all those parts, hybrid motor, into this rocket. And so and Harry can ask or agree that it's probably going to weathercock more, and you might get some wallowing. Wallowing to me is the rocket. It doesn't really want to go where you pointed it. It's trying to correct it. It has enough correction, but it's kind of wallowing. And about the time you think it's going to come apart, your motor, burnouts ends, and then you're safe. So it might do some wallowing. I would start getting concerned over 3.5.
Thank you. I think that answers the next question that's in there.
I think if I did in the front.
Sorry.
Do you agree with that, Harry?
I think. Yeah, and he also brings up a next question about 2.5 outside the range. I think in the rules it's not supposed to be over 2.5, if I remember right. So, a little thing on our rules, that some of the rules we have are more confining than NAR or AAA, like our speed off the rail. Are maintaining, this and that and the other thing. In NAR and AAA, people are flying H motors and cardboard rockets, and it really doesn't matter that it kind of comes off the 6-foot rail a little bit slow. But a 180-pound rocket flying on a P motor coming off the rail a little bit slow is concerning to us. AAA has a thing, and NAR has a thing. If the wind is 20 miles an hour, you have to stop. We've stopped at Spaceport when it was been 12 miles an hour for the speed and the direction of the wind. I was not able to point, I'm not using the word aim, point the rockets in a direction away from hazards well enough to make me comfortable. And so at 12 miles an hour, we shut down the range just because of the direction and the speed. We couldn't overcome any angling and pointing that we did. They just kept coming the wrong way. Did that answer that question?
I think so. I don't have any Q&A in the channel at the moment. Did you want me to share any of the documents or images that you have?
Look, I just opened up the electronics on this, and I'm going to pull out the electronics board, I hope.
That'd be great.
don't expect too much. I'm a simple guy, okay?
But while he's pulling that out on the tape, when you bring it up to the final inspection, if I find a joint that's supposed to come apart that's loose that I can pull apart real easily, I'll be asking you to put tape on it to make it tighter.
I'm going to talk about payloads here before I show you my amazing electronics board. That I'm a rocket guy. I like science and all, but I'll build a rocket for anybody's payload. I'd much rather have that payload stay in the rocket instead of me trying to dump it out somewhere. Dumping them out causes issues with recovery gear. If you can, take it out with the nose cone. It's easy to put a chute on the nose cone, your payload, and get them to separate and keep your electronics and your main parachute, everything with the rest of the rocket. The other thing with the payloads is, are they going to slosh around, move around to change the center of pressure, center of gravity? Those are the basic questions. You know, quite often, hey, do you want to see what we're doing? It's like, no. Is it staying in the rocket? Yeah. Is it moving around? Is it sloshing around? Is it going to create a fire or a hazard? No, don't care what you're flying. You know, and I'm not being conceited. I just have more on my mind about the rocket flight than I am about learning about your project. So when we look at your electronics, we're trying to figure out wiring colors, if batteries are secure, if they go to the right thing, etc. And so I have two electronics in this 6-inch. Were you able to figure out what wires went to what and where the switch was? Pretty simple. Other side, battery, secure, screw switch. Simple.
And is that just a wood mounting board? What is your mounting material?
It's basswood. And I don't know that this would be appropriate for a competition rocket. And the little screws, the Allen heads, are Dubro #2 wood screws. And the standoffs are 3/16 neoprene fuel lines for like model airplanes.
Yeah.
And you just cut them as long as you want. And then the screw switch is, I have a friend that prints them up. They have actually a little military surplus thing inside, but they work.
And a question did come up. Can payloads be deployed on their own chute at apogee, like at 10,000?
Yes, and well, maybe. So we realize that payloads are changing, drones are a thing, collapsible drones that come out and fly away on their own to a predetermined spot are great payloads. For rocket people, there's a lot of stuff that can get tangled up with that main parachute and stuff. So I have in the past, with special permission, allowed things to be deployed at apogee or before they got to that 1,500 foot. And I think next year's rules will allow a little more accommodations for those types of projects. As the safety guy, and I take the safety super serious. You know, whenever I say that, I get chills down my back and stuff. So I'm dead serious about safety, but I want everybody to fly. And so if you come to me and say, hey, we want to deploy this little folding up thing at 11,000 feet, and it's going to be on a drogue to a certain point, and then the wings or propellers are going to come out and it's going to fly away. It's like, can I see that thing at 10,000 feet? About to take your parachute off and they put a 30-foot nylon red streamer on there and a 90 decibel screamer of an audible device. At least we can have an idea of where the thing is coming in or coming down at and have a better chance of getting out from underneath it things don't go right.
Well, and the question was asking specifically if they could use a chute to deploy at 10,000. I think the concern would be that it would travel too far, because if you're using a chute on payload 10,000, it's going to be gone, right?
So if you were to contact me and Andy and stuff, why do you want to do that? Why we don't want you to do that, because if that parachute is too big and the wind is blowing right and it floats over to White Sands Missile Range, you will not get it back unless you want to pay some like $10,000 for them to go look for your rocket. And we do not want to start populating White Sands Missile Range with our misguided stuff. And so if you have an absolute good reason for needing your project to do that, and you have some built-in things saying, oh, it's not coming down at 25 feet per second, it's coming down at 65 feet per second, so that we can try to stay in more. And maybe on the flight safety review form, I'm prepared. On this thing here, I think down in the middle here, it talks about provisional. We may give you a provisional launch saying, we'll let you do that, but the wind has to be in our faces, which is bad, but it's away from White Sands Missile Range, and we'll fly it. But if you don't if we don't have those conditions, you won't be able to fly your project. And so, is that helpful?
Yeah, and I can, here we go. I've got that up here if you wanted to see the flight safety review.
Thank you. Holly, while you're there, if you can pull up the shackle.
Absolutely. Might have to tell me which one's the shackle. I've got the charcoal.
Actually, maybe it's Quick Link. No. It may have been the ones with a link or shortcut instead of an actual thing. So, all right, we're good. Here, I'll show a Quick Link. Quick Link.
Yeah.
Okay, we're going to talk about hardware and shock cords right now. So, in my opinion, one of the better shock cords for the price and what it can do for you is 1-inch tubular nylon. You can get it all around the world, I believe. And it's rated at about 4,200 pounds breaking strength. It has about, I think, 10% stretchability to it. It doesn't like heat all that well. And so a simple way of doing things is, because it's tubular, is feed another piece, like an overcoat, where it would come in contact with your charges. Or I was saying earlier, we can just wrap duct tape around your shock cord and protect it from your charges. So this Quick Link here, I believe, is 1,700 pound Quick Link. You would need 3 of these on your attachment point. To be compatible with the value or the breaking strength of this. This is a water knot. It's something like 95% the strength of the ability. It's basically an overhand knot with another overhand knot. Somewhere I put a link of how to tie knots in 1-inch nylon cord. Do you actually need Quick Links? They're the weakest link, literally. You have to use a whole bunch of them, and they cost money, they take up space. Knots work.
Yeah, and you can see that in the chat window. If anyone scrolls up, you can see that link that Tony put for us.
So we'll talk about some hardware again. This part up here is called an eye nut. 5/16, and this loop of Kevlar is held to the eye nut by a zip tie. Believe it or not, this, whether it was an eye bolt or an eye nut, can easily undo itself even when it's put on with tools. The fin can has a lot of area. It starts spinning up on its way down. It gets some twists, it gets some knots, and there becomes resistance on this. I've had it happen to myself twice. I'm not the smartest guy. Sometimes things have to happen to me multiple times before I finally get that light bulb that goes on going, hey, do something about this so that it doesn't keep doing that and stuff. So the easiest, simplest way is to simply drill a hole in here, tie a nut on the shot cord or on this Kevlar, because this will, it will unturn a little bit, but there's a stopper. There's no way that zip tie is going to break or anything. I can tie this knot in about 4 minutes. I can put black tape over it if I thought it was going to slip or come undone. Do you really need quick links, which add another failure point, more money, more weight into your system? So we're going to talk about ejection charges. So I've done a lot of research, studying, and experimenting with ejection charges. I was the guy that came up with the latex tubing ejection charge, and they work about 90% of the time. The problem is I do not know why they do not work that 10% of the time, and that concerns me. Kurt Von Delius, who is an Aeropack member, does a lot of high altitude stuff, and he still uses latex tubing. I have a picture that I can post. I'll post some stuff on HeroX in one of the chat forums type of thing. He's flown to 244,000 feet using latex tubing. And it works for him, and I'm not sure what he does a little bit different. And so I should back up a little bit. That black powder ejection charges work very well, but once you start getting up around 25,000 above mean sea level, they start becoming less efficient. And I think it's because of the black powder gets scattered and you don't have that continuous burn from one grain of black powder to the next. And so maybe at 27,000 feet, 5% of the grains aren't getting burned, they're getting scattered. And you go up to 35,000 feet, maybe 10% of those grains are getting scattered before they get burned and stuff. And yes, you have recovery gear and stuff around them, but it's still getting scattered and unused. And so this is just a simple PVC cap, and people will take and drill a hole in the bottom, put an E-match in the bottom, fill it up with black powder, and tape it off. And the process is that when that E-match goes off, what happens to that black powder? It comes boiling out of here, unburned, a big fountain of black that's burning on the top, but then it's starting to scatter. And there's a couple of great videos. I have a document, a Word document that I think it's called Vinyl Tubing High Altitude Charges or something. And there's links in there of somebody that some 8-ounce charges, and all you see is a big black volcano of unburned BP. So then a simple thing they did is took that E-match from the bottom and put it on the top. Now when it burns, everything underneath it has to get past that flame front. And so think about this as an old military cannon, the little short fat cannons that they were shooting at people running towards them. So what I came up with is a nice long barrel gun. This is I think it's 3/8 vinyl tubing. There's a plug in one end, and in this document you'll see these better. This is the black powder here. This tape is just holding the wire in place. Actually, this other one is a little bit easier to see. Yep. So that's a picture of it going off. That was, I think, 0.75. There you go. Thank you, Holly. And stuff. So the idea behind these is that it's like the barrel of a gun, that I have, kind of where the bullet would set. I have a little bit of dog barf in there to cushion it, and I'll talk about cushioning in a minute. The black powder's there. The E-match is on top of the black powder, and then some more dog barf just to hold. The tape that you see on the very top is not to keep the air inside or anything. It's just to keep the E-match from pulling out. There, just hold that. Oh, back up. And so the idea is that the E-match on top goes off on top of the black powder. Now anything underneath it has to bypass it before it comes out of the barrel of that gun and stuff. And so Jim Jarvis came up with this, and again, I'll put his link up. Jim Jarvis has been flying high longer than anybody else I know, higher in altitude. So he uses 1/8" brass tubing, and I got some of the brass tubing and did up some testing. And in Jim's write-up, he says that charges are violent. They are extremely violent, and I'm afraid to put them in my rockets and stuff. So I tried to figure out a way that simulated his ideas of being a long barrel and cushioning it by having the gun barrel a little bit rubbery, having that plug in there, and cushioning it with the dog. Dog barf is a blown-in insulation for homes. It's used for protecting parachutes and stuff. And so in my testing, in these vinyl tubing charges, it consumes it 100% of the time. And my test chamber is a 6-inch PVC pipe that's 4 feet long. And so I did a 3-inch rocket with a payload bay that slid, and it weighed 6 pounds with shear pins. And when I put the first vinyl charge in there, it blew the payload all the way through the rocket body and blew the top off my test chamber. And it was like, I'm onto something. I think it's better and stuff. So, and probably next year, teams that fly in the 30K and the demo flights are going to have to prove to us, or at least tell us about your deployment system. And truly, in rockets, all these things are systems. The fins are a system. The shape of the fin, the material, how they're attached, where they're attached, it's a system. And same thing with our deployment charges. It starts with, are you using CO2? Where are you putting it? How are you activating it? It's a system. And a long time ago, I found out that if any little thing in this flight goes wrong, usually your whole flight gets screwed up, and it becomes expensive and scary at times. So, going back. And so with this being the worst charge, I believe, I actually use balloons or the gloves of fingertips in all of my main charges, because at that altitude that I'm flying at, scattering it doesn't really matter to me. It's a constant and stuff. And so I just use regular balloons for the charges and stuff, and then I write on them. They're doubled over and stuff. One problem I was having, that if I'm truly, when I do STEM with my local high school, some years I use a lot of electronics, and I like test flying them before time. So I'll put 4 electronics in a rocket test flying. Well, that's a lot of charges hanging out together. If you have this many charges this close, this charge going off may set that charge off. Put 2 or 3 layers of duct tape over each of these other charges to protect them from the first charge. And it won't influence the other charges going off. It will just protect them from that initial charge going off. Let's talk about electronics for a minute. How much time do we have?
Looks like a minute.
A minute? If you're the electronics, am I muted or are you Kelly muted?
No.
Oh.
I hear you.
I did share that document in the chat for the group, but if you want to post it as well in the rest of the forum.
It can't be too many places. If you're the person that is in charge of your electronics for your rocket, does Ezra provide a ladder tall enough to get to where you need to go, or do you need to bring your own ladder? Do you have the right tools? When you get up on that ladder, what are you listening for? Do you know when you're on that ladder? You should know before you get on that ladder. Are you listening for 3 fast beeps, 1 fast beep, 7 long beeps? Know what you're listening for before you get on that ladder, so that when you don't hear them, you know something's wrong. Have the instructions with you, not on the laptop, but written down somewhere, so that when you're on that ladder, you can be looking up, oh, 7 means our battery's dead. So know how to troubleshoot from the ladder with the right paperwork.
Harry, do you think we have time for one last question? Do we want to push?
Yes. Have your checkoff sheet with you. Don't forget to put everything on your checkoff sheet that you don't know about. I'm done.
All right. Our team currently uses black powder burritos with duct tape. If we move to a 30K, should we implement a different method similar to the one shown?
No. Test what you're currently doing. Well, does it change with altitude? To get a vacuum pump and set up a little test chamber and stuff and figure out, oh, what's all those little black crumbs in the bottom? It's unburned black powder. Test it. I'm pretty positive it's not going to work. It's going to change the higher you get it. Stuff. So,
great.
Harry, would you like to talk about your RSO stuff? I'm sorry, I took all your time.
Well, mine's fairly simple. You know, once you've gone through all the other tests, by the time you get up to me, it should be. I'm just going to make sure that you have your. Be sure to bring your flight safety review signed off, and then your flight card that's all signed off. Have an appropriate igniter. We need dual igniters, something like this. I have seen a couple of people come up with a pair of E-matches. This won't work. You'll be sent off to get a igniter that'll work. And then I'll go through, make sure the motor's retained. The slip joints are a tight fit. Couplers are all screwed down. You know, everything is the way it should be. And if you do have a payload that you need to get to, try to fix it to where you can get to it and turn it on and get things buttoned up as quickly as possible. When the rocket arrives to me for that last final check, it should be ready to go on the pad without having to do basically anything more to it.
It's amazing what things Harry does find that passes by all of us, literally. And he finds them and calls me over, and it's like, how did that get past us? And one of the sayings we have out at Spaceport, for anybody that's out there, if you see something that's wrong or you're not sure about, say something to somebody. If you see something, say something.
Yep, great. All right, thank you both very much. If anyone has any other questions, they can reach Tony or Harry through the event main page under people. You can ask them questions directly, ask to connect with them. Thank you so much today. Oh, we've got one more question. We are out of time.
Yes, yes, even the COTS motors.
All right, it says, do you want 2 igniters in the rocket for the first ignition attempt, even in COTS motors?
Yeah.
The answer is yes.
We went from a really terrible thing with attempts, because people are putting E-matches in an end motor. It's like an E-match is not going to light an end motor without something attached to it and stuff. As soon as we went to dual igniters and people were having to figure out what that meant and build them or buy them, we're like at 99% success rate on that first igniter. And it really keeps the program going along.
That way, if one igniter is bad, the other one hopefully will fire it off.
See redundancy.
Mm-hmm. It's just redundant.
All right, thank you so much. I'm gonna go ahead and close this session, and hopefully we'll see you guys at some other sessions today.
All right, thank you.
Thank you.
Bye.